Welcome to Math with Mr. J.
In this video, I'm going to cover terms in algebraic expressions. Everything from what terms are, to identifying and counting terms, to like terms, and combining like terms. Feel free to check the description for chapters and timestamps if you would like to see and jump around to different parts of this video. We're going to start with an introduction to terms. So what terms are? Then move to identifying and counting terms. And then we will end with like terms. So what like terms are and combining like terms. Now simply put, terms are the parts that make up an expression. Terms can be numbers, variables, or a combination of both. Terms are separated by addition or subtraction signs. In order to better understand terms, let's start by looking at some examples. Now, I mentioned numbers can be terms, so some examples would be 8, 100, or -17. And it's as simple as that as far as numbers go. When we just have a number as a term, we call these constants or constant terms, because their value doesn't change, it remains constant. Next, we have variables. Some examples would be x, a, and g cubed. Terms can involve exponents, so something to keep in mind. Now, the value of variables can vary. The value can change. For example, x can equal 5, 30, or whatever the case may be in the given algebraic expression. And then lastly, we can have a combination of numbers and variables. For example, 2x. So a number times a variable, 2 times x. Or -14z. So a negative times a variable, -14 times z. We can even have variables times variables. For example, xy, x times y, or more than two variables. For example, x, y, z, so x times y times z. We can also have numbers, variables, and exponents, so something like 7a, b to the power of 4. So 7 times a times b to the power of 4. Or another example would be -21 x squared. So -21 times x squared. And my last example is x over 4. So x divided by 4. Now keep in mind, this can be rewritten using multiplication. X over 4 is equivalent to 1/4 x, or 1/4 times x. So just something to be aware of. I also want to mention that a number in front of a variable or multiple variables is called a coefficient. For example, for 2x, 2 is the coefficient. For -14z, -14 is the coefficient. Now, all of those are examples of terms. Remember, terms are separated by addition or subtraction signs. Let's move on to numbers 1 and 2 on the right side of the screen, where we will identify terms in the algebraic expression. So we're going to put this all together. Let's start with number 1, where we have 14x plus 3. Now again, terms are separated by either addition or subtraction. So let's look for parts of the expression that are separated by addition or subtraction. For example, we have 14x and then an addition sign. So 14x is a part or term of this expression. We then have that addition sign that we mentioned and then a 3. So 3 is our second term, and that's a positive 3. A term will take the sign of whatever is in front of it. We have an addition sign, so that 3 is positive. So we have 14x and 3, two terms in that expression. Let's move on to number 2, where we have 7ab to the power of 5 minus 2b plus 19. So let's look for the terms, the parts of this expression, starting with 7ab to the power of 5. That's followed by a subtraction sign. So this is our first part or term, 7ab to the power of 5. We then have that subtraction sign and 2b. So this is our second part or term. And remember, it takes the sign that's in front. So this is a negative 2b. That's our second term. And then lastly, we have plus 19. So an addition sign and then 19. So 19, a positive 19, is the last term. So this expression has 3 terms, 7ab to the power of 5, negative 2b, and 19. Now, one thing I do want to mention about subtraction and negatives is something you can do to an expression to make it a little simpler to identify any negatives and terms in general, and that's to make everything addition. So what we can do, we can separate all of the terms only by addition, and we do this by rewriting all subtraction as adding the opposite. For example, let's rewrite number 2 using addition to separate the terms. So we need to find any subtraction and rewrite that as adding the opposite. We are subtracting 2b, so subtracting a positive 2b. So we need to add the opposite. So add negative 2b. Adding negative 2b is equivalent to subtracting positive 2b. So let's rewrite this expression down below. 7ab to the power of 5 plus negative 2b plus 19. Both of those expressions are equivalent. The terms are still the same. 7ab to the power of 5, negative 2b, and 19. So again, that's a strategy you can use to turn everything to addition and separate the terms that way. The benefit is that all of the terms will only be separated by addition. Therefore, it's a little simpler to identify all of the terms, especially the negative ones. So there are the basics about what terms are. Let's move on to more examples. Here are more examples where we will take a look at identifying and counting terms. Let's jump into number 1, where we have 6y plus 2. So we need to look for the terms that make up this algebraic expression. We start with 6y and then an addition sign. So we can see that this is the first part, the first term of that algebraic expression. So 6y is a term. Then we have an addition sign and then a 2. So 2 is the next term, and that's a positive 2 because a term will take the sign that's in front of it. So 6y and 2. So for number 1, that algebraic expression has 2 terms, 6y and 2. Let's move on to number 2, where we have 7m to the power of 5 plus negative 2n plus 10. So let's look for the terms that make up this algebraic expression. We start with 7m to the power of 5 and then an addition sign. So we can see that this is the first part, the first term. So 7m to the power of 5. Then we have plus negative 2n. So this is the second term, negative 2n. And then we have an addition sign and then a 10. So we end with this 10 here, and it's a positive 10. So for number 2, we have 3 terms, 7m to the power of 5, negative 2n, and then 10. You can see that the terms are separated by those addition signs. Those are the parts, the terms, that make up that algebraic expression. Let's move on to number 3, where we have 4xy cubed. So for this algebraic expression, we don't have any addition or subtraction signs. So this is actually one term. We only have one term here, 4xy cubed. And that's okay. We can have algebraic expressions that are just one term. Lastly, let's move on to number 4, where we have 4ab plus 2a minus 8b minus 3. So let's look for the parts, the terms that make up this algebraic expression. We'll start with 4ab. So we have 4ab and then an addition sign, so we can see that this is our first term. Then we have that addition sign and then 2a. So 2a is the second term, and it's a positive 2a. And then we have a subtraction sign that separates the 2a from the next term, where we have 8b. So we are subtracting 8b. Again, terms take the sign that's in front of them. So this is a negative 8b. And then lastly, we are subtracting 3. Again, take the sign that's in front. So this is a negative 3. So for number 4, we have 4 terms. 4ab, 2a, negative 8b, and negative 3. Now, before we end here, I do want to mention one more thing, and it's about rewriting algebraic expressions using only addition. This will make it a little simpler to identify terms, especially the negative ones, because everything will be separated only by addition. Now, we can rewrite algebraic expressions using only addition by rewriting subtraction as adding the opposite. So for example, where we subtract 8b, we need to add the opposite. We are subtracting a positive 8b, so let's add the opposite. The opposite of a positive 8b is negative 8b. Then we are subtracting 3, so add the opposite there. We are subtracting a positive 3. So let's add the opposite. So adding a negative 3. That's equivalent to subtracting 8b and then subtracting 3. So let's rewrite that algebraic expression. I'll come below here. So we have 4ab plus 2a plus negative 8b plus negative 3. So those two expressions are equivalent. We're not changing the value of anything. We're just changing everything to addition. Again, by changing subtraction to adding the opposite. And you can see that we have the exact same terms. 4ab, 2a, negative 8b, and negative 3. So it's a strategy to keep in mind. You don't have to do that, but again, something to keep in mind. So there's how to identify and count terms. Let's move on to an intro to like terms. Let's take a look at this introduction to like terms. Now, simply put, like terms are terms with the same variables to the same powers. So same variables, same exponents. Now keep in mind, coefficients, the numbers in front of the variables, do not have to be the same. So again, like terms, same variables to the same powers. We will start by taking a look at some like terms and then also some unlike terms. Then we will move to identifying like terms within algebraic expressions. Let's jump into number 1 and start with the like terms where we have 14a and 9a. So we have the same variable of a in both of these terms. These variables are also to the same power, so these are like terms. Remember, the coefficients do not have to be the same. Now, as far as these variables being to the same power, if no exponent is shown, that just means there is an exponent of 1. So something is to the power of 1. Anything to the power of 1 is just itself, so we typically don't include that exponent of 1. It's not needed. So that's something to keep in mind. So 14a and 9a are like terms. As far as the unlike terms, we have 14a and 9b. These two terms have different variables, so they are unlike terms. Let's move on to number 2, where we have 7x squared and 2x squared for the like terms. Now, these two terms have the same variable of x to the same power of 2, so these are like terms. Now, for the unlike terms, we have 7x squared and 2x. We have the same variable of x, but for 7x squared, that x is to the power of 2, and then for 2x, that x is to the power of 1. So these are unlike terms. Let's move on to number 3, where we have 5 and 3 for the like terms. These are called constant terms. We just have numbers. They are called constant terms or constants because their value stays the same. It stays constant. There aren't any attached variables that can change the value of these terms. So whenever we just have numbers, constant terms, they are going to be like terms. So 5 and 3 are like terms. As far as the unlike terms, we have 5 and 3y. We don't have the same variables to the same powers, so these are unlike terms. Moving on to number 4, we have 6xy cubed and xy cubed for the like terms. So we have the same variables of x and y to the same powers. X is to the power of 1 and y is to the power of 3. So these are like terms. Same variables to the same powers. Now, as far as xy cubed, there isn't a number in front, so it looks like we don't have a coefficient. But if no coefficient is shown, then the coefficient is 1. We have 1 of whatever follows. So technically, this is 1xy cubed. And we can always put that coefficient of 1 in if we would like. But again, if no coefficient is shown, then the coefficient is 1. Now, as far as the unlike terms, we have 6xy cubed and x cubed y. We have the same variables of x and y and the same exponent of 3, but these are unlike terms. We don't have the same variables to the same powers. 6xy cubed has x to the power of 1 and y to the power of 3. X cubed y has x to the power of 3 and y to the power of 1. So 6xy cubed and x cubed y are unlike terms. We have the same variables, but they're not to the same powers. So those are some examples of like and unlike terms, and then why they are like and unlike terms. Let's move on to numbers 5 and 6 and identify like terms within algebraic expressions. Starting with number 5, where we have 10x plus 3x minus 8. So are there any like terms within this algebraic expression? Yes, 10x and 3x. These two terms have the same variable of x to the same power of 1. So 10x and 3x are like terms. There are 3 total terms in that algebraic expression, and 2 of them are like terms. Lastly, let's move on to number 6, where we have 15c squared plus 10d plus 3c squared plus 2d. So do we have any like terms within this algebraic expression? Yes, let's start with 15c squared. So we have the variable of c and then an exponent of 2. 3c squared has the same variable, c, to the same power of 2. So 15c squared and 3c squared are like terms, the same variable of c to the same power of 2. So 15c squared and 3c squared are like terms. Then we also have 10d and 2d, same variable of d to the same power of 1. Let's box in those like terms in order to separate them from the other like terms that are circled. So 10d and 2d are also like terms. So out of the 4 terms in that algebraic expression, we have 2 pairs of like terms, 5c squared and 3c squared, and then 10d and 2d. So there's an intro to like terms. Let's move on to more examples and identify more like terms. Here are more examples where we will continue to take a look at like terms. Let's jump into number 1, where we have 6 terms listed. Now, there are going to be 3 pairs of like terms, so everything has a matching like term here. We'll start with 7x. Now, 7x has a coefficient of 7 and then a variable of x, so we need to find another term with that variable of x. Remember, coefficients, the numbers in front of the variables, do not matter when it comes to whether terms are like terms or not. So let's box in 7x, and then the like term is going to be 4x. Both of those terms have that variable of x. I do want to mention that if no exponent is shown, then there is an understood exponent of 1. So something is to the power of 1. Anything to the power of 1 is just itself. So we typically don't include the exponent of 1. It's not needed. So for 7x and 4x, those variables are to the power of 1. So we have the same variable of x in those terms to the same power of 1. Next, we have 10. This is called a constant term or constant because the value stays the same. It stays constant. There aren't any attached variables that can change the value of this term. So let's circle 10 to keep it separated from the other like terms. And then the like term is going to be 8. 8 is also a constant term. So constant terms are like terms. And then lastly, we have 7y and y. So they share that variable of y, and there isn't any exponent shown. So again, these are to the power of 1. 7y and y are like terms. We can use triangles to separate that pair of like terms from the other pairs of like terms. Now, as far as this term right here, y, if no coefficient is shown, then the coefficient is 1. We have 1 of whatever follows. And we can always write that coefficient of 1 in front of the variable if we would like. So that's technically 1y there. So something to keep in mind as far as coefficients. Let's move on to number 2, where we have another 3 pairs of like terms. We will start with negative 3ab. So let's box in negative 3ab and find the like term. So we need those variables of a and b. And both of those variables are to the power of 1. So the like term is 5ab. Next, we have 9a cubed. So we need a variable of a to the power of 3. So let's circle this term. And then the like term is going to be negative 12a cubed. So you can see that variable of a to the power of 3 make those like terms. And then lastly, we have a cubed b. So we have that variable of a cubed, so a to the power of 3. And then we have that variable of b, which is to the power of 1. The like term is going to be 2a cubed b. Now again, For this term right here, a cubed b, since no coefficient is shown, that means the coefficient is 1. So we can always rewrite it with that coefficient of 1 if preferred. Let's move on to numbers 3 and 4, where we will identify like terms within algebraic expressions. Starting with number 3, where we have 9y plus 5 plus 5y plus 2. So are there any like terms within this expression? Yes. Let's start with 9y and 5y. Both terms have that variable of y to the power of 1. So 9y and 5y are like terms. We also have two constant terms, 5 and 2. So let's box those in to separate them. 5 and 2 are like terms. So we have two pairs of like terms within that algebraic expression. Lastly, let's move on to number 4, where we have 7x squared plus negative 3xy plus negative 3 plus x squared plus 14xy. So do we have any like terms within this algebraic expression? Yes. Let's start with 7x squared. So we have a variable of x to the power of 2. X squared has a variable of x to the power of 2. So 7x squared and x squared are like terms. Next, we have negative 3xy. So let's circle this term in order to separate it from the other like terms. We have a variable of x and a variable of y. So we have two variables, and both of them are to the power of 1. 14xy also has the variables of x and y to the power of 1. So negative 3xy and 14xy are like terms. And then lastly, we have a constant term of negative 3, but we don't have any other terms left, so there aren't any more like terms. We are done. We identified all of the like terms. So there's how we identify like terms. Let's move on to an introduction to combining like terms. Let's take a look at this introduction to combining like terms. Now remember, like terms are terms with the same variables to the same powers. When we combine like terms, we look for any like terms in the given algebraic expression and combine them into one term. By combining like terms, we can simplify expressions. That just means we can rewrite the original expression in a simpler and easier way to understand and work with. Let's jump into number 1, where we have 9x plus 3x. We will start with this basic expression and work our way up. So we have two terms in this expression, 9x and 3x. Both terms have the same variable of x, and these variables of x are to the same power. Remember, when we don't have an exponent attached to a variable, there is an understood exponent of 1. Anything to the power of 1 is just itself. So 9x and 3x are like terms. Now, when we combine like terms, all we need to do is add or subtract the coefficients, the numbers in front of the variables. The coefficients in number 1 are 9 and 3. We have a positive 9x plus a positive 3x, so let's add those coefficients. 9 plus 3 is 12, and then we have the variable of x. And that's it. We took those two like terms, 9x and 3x, and combined them into one term, 12x. 12x is equivalent to 9x plus 3x, so we didn't change the value of the expression. So 12x is our final simplified expression. Let's move on to number 2, where we have 8g plus 7 plus 5g plus 2. Are there any like terms that we can combine in order to simplify this expression? Yes, we have 8g and 5g. Both of those terms have that variable of g. And then we have constant terms, 7 and 2. I'll box in the constant terms to separate them from the 8g and the 5g. Now we can combine like terms. We have 8g plus 5g. That gives us 13g. And then we have 7 plus 2. That gives us 9. So we end up with 13g plus 9. And that's our simplified expression. That expression of 13g plus 9 is equivalent to the original expression. We were just able to simplify the original expression by combining like terms. We started with 4 total terms, but we were able to combine like terms, and now we only have 2 total terms. Let's move on to number 3, where we have 6y squared plus 10y plus 2y squared plus 3y plus y. Let's find any like terms that we can combine. We'll start with 6y squared. 2y squared is a like term. Both of those terms have that variable of y to the power of 2. Now, do we have any other like terms within this algebraic expression that we can combine? Yes, 10y. And I will box these terms in order to separate them from the y squared terms. 3y. And then y. Now, I do want to mention this term right here, the y, the variable by itself, the coefficient is 1. We don't have a coefficient written in front. Whenever you see that, the coefficient is 1. There is an understood 1 in front of a variable, and it can be helpful to write that 1 in there when you combine like terms. So you can always write that 1 if you would like. Now, since this algebraic expression has 5 terms and we are working our way up to more complicated algebraic expressions, we're going to use a strategy to help us organize the expression before we combine like terms. We are going to rearrange and rewrite the expression and put the like terms next to each other. I'll start with 6y squared plus the like term of 2y squared, plus, now we have the y terms, so 10y, plus 3y, plus 1y. So now all of the like terms are next to each other, and it's a little easier to see what we can combine. So this is a strategy to keep in mind. Now, do you have to do this step in order to combine like terms? No, but it can be helpful. Now we can combine like terms. We will start with 6y squared plus 2y squared. So add the coefficients. 6 plus 2 is 8. And then we have y squared plus, now we can combine the y terms. So we have 10 plus 3 plus 1. 10 plus 3 is 13, plus 1 is 14. So we get 8y squared plus 14y. And that's the simplified expression. We now have an equivalent expression that is simpler than the original. We simplified the expression. We went from 5 terms to 2 terms. Let's move on to number 4, where we have 7x plus 2y minus 4x plus 2y. Let's find any like terms that we can combine. We will start with 7x and negative 4x. Now, when we combine like terms, a term is going to take the sign that's in front of it. So this is negative 4x. Then we have 2y and 2y. So let's box those terms in order to separate them from the x terms. Now we can rewrite this expression with the like terms next to each other. We will start with 7x minus 4x. So we have a negative 4x there. Make sure to bring the sign that's in front of the term with it when we rewrite the expression. Plus 2y, so now we have the y terms, plus another 2y. Now we can combine like terms. So we have 7x minus 4x, or you can think of this as 7x being combined with negative 4x, however you want to think about it. 7 minus 4 is 3, and then we have the x, or if you're thinking about it as 7x combined with a negative 4x, 7 and negative 4 give us 3 as well. Then we have our 2y plus 2y, that gives us plus 4y. So we end up with 3x plus 4y, and that's our simplified expression. We went from 4 total terms to 2 total terms by combining like terms. 3x plus 4y is equivalent to the original expression. We were just able to, again, simplify this expression by combining like terms. Now, I also want to go through simplifying this expression a slightly different way to start off, and that's by rewriting the original expression with only addition separating the terms. We do this by changing any subtraction to adding the opposite. The benefit of having all terms separated only by addition is that it's a little simpler to identify all of the terms, especially any negative terms. It kind of organizes the expression and helps any negatives stand out. I'll rewrite the expression off to the side here. So 7x plus 2y minus 4x plus 2y. So let's rewrite subtraction as adding the opposite. So adding the opposite of a positive 4x is a negative 4x. So adding the opposite. Let's rewrite the expression with that change. So we have 7x plus 2y plus negative 4x plus 2y. Let's rewrite that expression with like terms next to each other. So 7x plus negative 4x plus 2y plus 2y. Now we can combine like terms. We have 7x plus negative 4x. That gives us 3x. And then we have 2y plus 2y. So that gives us plus 4y. 3x plus 4y that way as well. So that's just another strategy to be aware of. So there's an intro to combining like terms. Let's move on to more examples and continue to work on simplifying expressions by combining like terms. Here are more examples of expressions that we can simplify by combining like terms. Let's jump into number 1, where we have 9c plus 6d plus 5d plus 8c plus 2d. The first thing that we need to do is identify any like terms that we can combine. So are there any like terms that we can combine in this expression? Yes. Let's start with 9c and 8c. Both of those terms have the same variable to the same power. Both terms have the same variable of c to the same understood power of 1. So they are like terms. Remember, when we don't have an exponent attached to a variable, there is an understood exponent of 1. Something is to the power of 1. Anything to the power of 1 is just itself. Do we have any other like terms that we can combine? Yes, we have 6d, 5d, and 2d. All of those terms have the same variable of d to the same understood power of 1. So let's box those terms in order to separate them from the other terms. Are there any other like terms that we can combine? No, all of the like terms have been identified. So what we can do now, we can rewrite this expression with the like terms next to each other. By rewriting this expression with all of the like terms next to each other, this will help us organize the expression. It will make combining like terms a little simpler. We have 9c plus 8c plus 6d plus 5d plus 2d. So now all of the like terms are next to each other, and it's a little easier to see what we need to combine. So this is a strategy to keep in mind. Now, do we have to do this step in order to combine like terms? No, but it can be helpful. Now we can combine like terms. Let's start with 9c and 8c. So we have 9c plus 8c. We need to add the coefficients, the numbers in front of the variables. So we have 9 plus 8, which is 17. So we have 17c plus, and now we can combine these terms. So we have 6d plus 5d plus 2d. 6 plus 5 is 11, plus 2 is 13. So we have 13d. And this is our final simplified expression, 17c plus 13d. Now 17c plus 13d is equivalent to the original expression. We went from 5 total terms in the original expression and simplified it to 2 total terms by combining like terms. Let's move on to number 2, where we have negative 10a plus 2ab plus 9a plus ab plus 9a minus 8. Let's start by identifying any like terms that we can combine. So do we have any like terms that we can combine? Yes, we have negative 10a and 9a and another 9a. All 3 of those terms have the same variable to the same power, the variable of a to the understood power of 1. Do we have any other like terms that we can combine? Yes, we have 2ab. Let's box these in order to separate them, and then ab. Now this term right here, ab, does not have a coefficient written in front. Whenever we see this, there is an understood coefficient of 1. So this is 1ab. And we're able to write that 1 in as the coefficient. And it's helpful to do so when combining like terms. That way you know you need to combine that 1. Are there any other like terms within this expression that we can combine? No, but we do have one more term, negative 8. So we have a constant term of negative 8, and I'll circle that term in order to separate it. Even though we don't have anything to combine it with, we still need to include it in the simplified expression. And that is negative 8. Remember, a term will take the sign that's in front of it. So we have negative 8 and negative 10a within this expression. Now we can rewrite this expression with the like terms next to each other. We have negative 10a plus 9a plus 9a plus 2ab plus 1ab minus 8. Now we can combine like terms. Let's start with negative 10a plus 9a plus 9a. Negative 10 plus 9 is negative 1, plus 9 is 8, a positive 8. So we have 8a, and then plus 2ab plus 1ab. 2 plus 1 is 3, so we have 3ab. And then lastly, we have a negative 8 or minus 8 here. So 8a plus 3ab minus 8 is our final simplified expression. We went from 6 total terms in the original expression to 3 total terms in the simplified expression by combining like terms. Let's move on to numbers 3 and 4, where we actually have the same exact expression, 4x squared minus 7 plus 3x minus 2x squared plus 3. We're going to go through this 2 slightly different ways. First, we will go through simplifying the expression as it currently is, and that's for number 3. For number 4, we're going to rewrite the expression so all of the terms are separated only by addition. We will talk more about that strategy once we get to number 4. Let's start number 3 by identifying any like terms. So do we have any like terms that we can combine? Yes, we have 4x squared and negative 2x squared. Both of these terms have the same variable of x to the same power of 2. So 4x squared and negative 2x squared. Remember, a term takes the sign that's in front of it, so that's negative 2x squared. Do we have any other like terms that we can combine? Yes, we have two constant terms, negative 7 and 3. I'll box those terms in order to separate them. And then lastly, we have 3x. We don't have any like terms to combine 3x with, but I will circle it in order to separate it from the other terms. Now we can rewrite this expression with the like terms next to each other. Remember, bring the sign that's in front of the term with it as you rewrite this expression. So we have 4x squared, and then negative 2x squared is the like term. So this is going to be 4x squared minus 2x squared. Then we have plus 3x, and then our constant terms last. So we have minus 7, a negative 7, plus 3. Now we can combine like terms. We have 4x squared minus 2x squared. Or you can think of this as combining 4x squared and negative 2x squared. However you want to think about it, you'll get the same thing either way. Let's subtract the coefficients. We have 4 minus 2, which gives us 2. Or if you thought about it as 4 combined with negative 2, that gives us 2 as well. So this is 2x squared. Then we have plus 3x. And then we can combine negative 7 and 3, positive 3. So we have negative 7 plus 3. That gives us negative 4. So our final simplified expression is 2x squared plus 3x minus 4. We went from 5 total terms in the original expression to 3 total terms by combining like terms. Let's move on to number 4, where we will take a look at a strategy we can use when we have subtraction or negatives involved in the expression. We're going to rewrite the original expression with only addition separating the terms. The benefit of having all terms separated only by addition is that it's a little simpler to identify all of the terms, especially any negative terms. It kind of organizes the expression and helps any negatives stand out. Now, do you have to use this strategy? No, but it can be helpful, so I wanted to at least go over it. So let's rewrite this expression with only addition separating the terms. We do this by adding the opposite, so change any subtraction to adding the opposite. Let's change this to addition, and then the opposite of positive 7 is negative 7, so add the opposite. Then let's add the opposite here as well, so the opposite of positive 2x squared is negative 2x squared. So let's rewrite this with those changes. So we have 4x squared plus negative 7 plus 3x plus negative 2x squared plus 3. So now all of the terms are separated only by addition. Now we can identify any like terms. We have 4x squared and negative 2x squared. Then we have negative 7 and 3, and then 3x. Now let's rewrite this expression with the like terms next to each other. So we have 4x squared plus negative 2x squared plus 3x plus negative 7 plus 3. Now we can combine like terms. We have 4x squared plus negative 2x squared. 4 plus negative 2 is 2, so we have 2x squared plus 3x plus -7 plus 3. -7 plus 3 is -4. So plus -4. Now this is correct, but we can clean this up a little bit, so to speak. We have a double sign. We are adding a negative 4. Adding a -4 is the same as subtracting 4. We are decreasing in value by 4, so we can rewrite this with just one sign. We don't need both of those signs. When we add a negative, that's the same as just subtracting a positive. So let's change this to subtracting 4. And again, getting rid of the double sign will make this a little simpler. It will clean it up. We can rewrite this as 2x squared plus 3x minus 4. And that's our final simplified expression. So you can see that we got the same exact simplified expression for number 3 and 4. Just slightly different strategies as far as organizing the expression to start. Now, I do want to mention one last thing, and it's about writing out expressions. When we write an expression, we typically want any exponents first. If there are multiple exponents, write them from greatest to least. If we have the same exponent, go in ABC order. And then constant terms always come last. So for example, in number 1, we have the variables of C and D. Both are to the understood power of 1, so we go in ABC order. For number 2, we have A and AB. Everything here is to the understood power of 1, so we go in ABC order. A comes first, then AB, and then the constant term comes last. For numbers 3 and 4, we have x squared, so the greatest exponent, 2. Then we have the variable of x to the understood power of 1. And then lastly, we have the constant term. So something to keep in mind when you are writing expressions. So there you have it. There's all about terms in algebraic expressions. I hope that helped. Thanks so much for watching. Until next time, peace.